Imagine a world where light behaves unpredictably, defying common sense. Light, which we often take for granted, suddenly becomes a mysterious entity, bending and twisting in ways that challenge our understanding. Imagine tiny particles, like photons, acting as both waves and particles. These photons can transform seamlessly, shifting between being a particle and a wave, depending on how we observe them. This is the strange world of quantum mechanics, a realm that challenges our understanding of reality. It's a world where the rules of classical physics no longer apply, and new perplexing principles take over. At the heart of this mystery lies a simple yet profound experiment, the double-slit experiment. This experiment reveals the dual nature of light and the fundamental principles of quantum mechanics. This experiment, first conducted in the early 1800s, continues to baffle scientists and philosophers alike. Despite its simplicity, it has profound implications for our understanding of the universe. It reveals the bizarre nature of light and matter, raising profound questions about the nature of reality itself. How can light behave both as a wave and a particle? How can something be in two places at once? This phenomenon, known as superposition, defies our everyday experiences and challenges our perception of reality. How can our observation influence the outcome of an experiment? This is the observer effect, a principle that suggests our mere act of observing can alter the behavior of particles. These are the questions we'll explore. Join us as we delve into the enigma of light and the mysteries of quantum mechanics. In the 19th century, long before the advent of quantum mechanics, the scientific community was abuzz with debates about the nature of light. A British polymath named Thomas Young set out to unravel the mysteries of light, challenging the established norms of his time. At the time, Isaac Newton's corpuscular theory of light, which described light as particles, was widely accepted. Young, however, suspected otherwise. He was intrigued by the idea that light might behave differently. He believed that light was a wave, similar to sound or water waves. This was a radical idea that could change the understanding of physics. To test his hypothesis, Young designed a simple yet ingenious experiment. He meticulously set up his apparatus to ensure accurate results. He shone a beam of light onto a screen with two closely spaced slits, a setup that would later become famous as the double-slit experiment. If light were particles, he reasoned, the light passing through the slits would create two distinct bright bands on a screen placed behind it. This was the expected outcome based on Newton's theory. Instead, Young observed something astonishing. The light formed an interference pattern, a series of bright and dark bands, revealing the wave nature of light. When Young shone the light through the two slits, he observed an interference pattern on the screen, a series of alternating bright and dark bands, which was quite unexpected. This pattern, he realized, was characteristic of wave interference, much like the ripples created by two pebbles dropped into a pond, merging and interacting. Light, it seemed, behaved as a wave after all, contradicting earlier beliefs. But the story doesn't end there, as more discoveries awaited. With the advent of quantum mechanics in the 20th century, physicists discovered that light can also behave as a particle, called a photon, adding to the mystery. This wave-particle duality, as it came to be known, is one of the most baffling aspects of quantum mechanics, challenging our understanding. The double-slit experiment takes an even stranger turn when we try to observe which slit each photon passes through. This simple act of measurement changes everything, revealing the mysterious nature of quantum mechanics. If we place detectors at the slits, the interference pattern disappears, and we observe two distinct bands, as if light were behaving as particles. This shift from wave-like behavior to particle-like behavior is both fascinating and perplexing. The act of observation, it seems, forces the light to choose between acting as a wave or a particle. This duality is at the core of quantum mechanics, challenging our classical understanding of physics. This phenomenon, known as wave function collapse, lies at the heart of the Copenhagen interpretation of quantum mechanics. According to this interpretation, the act of measurement causes the wave function to collapse into a single, definite state. This interpretation suggests that particles exist in a superposition of states, represented by a wave function, until an observation is made, at which point the wave function collapses into a definite state. This idea of superposition is one of the most intriguing aspects of quantum theory. The double-slit experiment, with its enigmatic results, forces us to confront a profound question. What is the nature of reality, and what role does our observation play in shaping it? This experiment continues to be a cornerstone in our quest to understand the quantum world and its implications for the nature of existence.